welcome. This is actually our second webinar in the series of 4 webinars. And last week we were speaking about energy simulation and introduce some basic concepts. And in today's webinar, we are going to be a little bit more detailed. We're going into detail. We'll be looking at an overview of how to set up a whole building energy model, and using BEopt. This is a software, simulation software, to perform a sample simulation. So just let me introduce myself here. I'm Manfred Zapka. I'm Principal of Sustainable Design and Consulting. And I'm also an adjunct professor at the School of Architecture, the University of Hawaii, where I teach and conduct research. And my research is applied research about energy efficiency in buildings and occupant comfort. And you can contact me at sustainabledc@gmail.com. Today's webinar will be as follows. The objectives will be just to illustrate the basic process steps of building performance simulation applications. And then we show a generic energy simulation workflow. And I will be introducing to you the energy simulation software BEopt, which is a really powerful and easy to learn simulation, and will be performing an example BEopt energy simulation. And afterwards, we will be discussing main simulation process steps and also point out what actually is what we have to consider. Again, like the central value proposition of today's webinar is to show a generic building energy simulation by using an easy to learn and use simulation software BEopt. Let me again, like last time, share with you my simulation story and my brief, my previous work in building performance and energy simulation. And I think most of us who are in the building design field have already done this visual renderings and for architectural renderings, so putting in indoor or external virtual renderings in order to enhance our design and marketing effort. And in addition to that, I've done a lot of building energy simulations. And here actually simulations is basically the same as modeling. And we again, I like the word simulation, but you will also hear a lot of times calling people people referring to modeling, but it's basically the same. I also have done here at the University of Hawaii and somewhere else is building mass flow energy simulation with CFD. And right now, lately, we've been getting into occupant comfort simulation, which is equally important. But today we are going to discuss the whole house simulation. So when we speak about the whole house simulation, we have to have two things. And one is actually we are looking at the electricity, which is provided to the building for direct use. And then we have something which is mostly the secondary concern here, but also very important, is how is the building performing in terms of heat. And we have heat coming in from the indoor. And again, we are speaking here only for Hawaii, where we have a hot and humid outdoor, and we want to achieve a cool and comfortable indoor environment. So the heat which comes in has then to be removed by some kind of device, and either it could be like a mechanical cooling device, or it could be naturally ventilated. So we have here, if we compare the energy use and heat processes, on the left side, energy use, and this is actually almost like bookkeeping. We have to consider all the energy uses, and then we have to add it all up. And the biggest challenge actually is to get everything, comprehensive accounting. You can actually do it by hand. It's possible, but it's much easier to use it with an energy simulation software. On the other side, it's much more complex, and we should always use a software is to look at the heat process and the heat performance of the building. And here we say heat is coming into the building, it's also generated inside of the building. And then we have to actually get the heat out. And here the objective is to determine the entire heat load which has to be removed from the indoor spaces by the AC. And then we, of course, need a lot of electricity for that. Therefore, it's so important, specifically here in Hawaii, where we have a lot of air conditioning, to consider the heat balance. So let's first look at how you would consider and how would you calculate the energy uses in the building. And here a little basic formula, which everybody knows, of course, is that you have the power, which is kilowatts, and you have to multiply the power, kilowatts, by time in order to get the energy. Power is also important for electric, performance of the building. But right now, because we are concentrating on the energy. So here I give you some examples, and let's go through that. It's always good to look back at the principles. And let's say we have an AC unit, a window, typical window AC unit, a power drain. Let's say it's 1.2 kilowatts. This would be similar to about 12,000 BTU per hour unit or 1 ton unit. We have the power. Now we have to consider the time. And let's say, just consider we have it on our 8 hours per day on a hot day, and we have 200 hot days per year. Then we would have 1,600 hours per year, which we have to account for. So the energy used is 1.2 kilowatts times 1,600 hours per year. So we have 1,920 kilowatt hours per year in Hawaii, where we have high energy cost. This would be $560 per year. This actually is the software is performing for this very, very easily, but we also could do it in pencil and paper or with our calculator. Next one is like a refrigerator, typical, and an Energy Star, an effective Energy Star refrigerator is typical, like 100 watts. It's 0.1 kilowatt. The time of operating, it's about 15 hours per day. It's not that we switch it off in the remaining time, but it cycles on and off. So we actually would have like 15 hours per day times 365 is 5,500 hours per year. The electric use is 0.1 kilowatt times 5,500 hours per year. We have 550 kilowatts, or here annual energy cost for that would be $160 per year. And just as a comparison, the light bulb, a very energy efficient CFL, is like 13 watts. We have it 6 hours per day on every day, and it comes down to it's about only $8 per year. So we see already the difference in terms of cost, energy cost. And it will also give you, once you're getting into the energy simulation or modeling, an indication where should we, concentrate our efforts in optimizing. If we look at the heat balance, you have outside hot and humid outside. We have the solar gain on the roof. We have solar gain on the walls. We also have solar gain through the windows. And so we have conduction, when we have a hot outside envelope. So air is getting through heat is going through the walls. And we have infiltration where through the cracks, hot air is coming in. These are external sources. Internal sources would be electric lighting, electric equipment, but even occupants. We actually, as human beings, we get off a lot of heat. And not only if we only argue, it's just normal. Just sitting there or just doing like a work or whatever, we actually putting out a lot of heat. So this is a heat we have to consider. And again, like, if we have an energy in simulation software, the software does that for us, which is of course convenient. And how do we remove the heat from the indoor spaces? We can do this by mechanical cooling if we have an AC. So you see heat is coming in. We would like to maintain a comfortable inside temperature. Also like a humidity, but right now we are only concentrating on sensible heat. And then the heat has to be removed. And here it has to be removed by mechanical means. And this, of course, needs a lot of energy remove. On the other side is with your natural ventilation, we have the nature. It's giving a puff here, it just creates wind. Wind creates pressure on the envelope, outside envelope, and therefore driving force of wind through the building. It could also be that, you know, of course, it's something like stack effect, where it is the wind movement or the pressure differential is due to buoyancy movement. But right now, let's consider the wind. So wind is going through here, and it takes out the air which is inside, it replaces it with outside air and gets rid of the heat. But usually only by doing this, the indoor space is always slightly warmer than outside. So there's a limit to how much heat we can remove. But the big advantage of it is that we do not have any energy to remove the indoor heat with natural ventilation. Let's look at the modes of heat transfer which we have to consider in the whole house simulation. We have convective heat transfer, we have conductive heat transfer, and radiative heat transfer. By the way, radiative doesn't have anything to do with dangerous radiation. Radiative means only like this is radiant heat transfer is through infrared radiation, which is of course not dangerous. So first of all, we have conductive heat transfer, and this means we need direct contact between objects for the exchange of heat. And let's say we have a wall, we have an outside hot outdoor, then the outside of the envelope heats up, and the heat goes always to the lower side, to the colder side. So here we actually have an outside warm layer, then we have some kind of insulation in between, and then we have a cool layer. So here we have some kind of a barrier, and the barrier is insulation. And you all have heard of an R value. So the R value in a wall is actually a combination of all the R value. Here we have a typical wood stud wall where we have an insulation in the middle. We have the wood studs, we have siding, so there are different layers. So the heat is going from the outside to the inside. Here in our climate. In the climate of the mainland, where we have cold climate, it would be the opposite around. Here's another illustration of what kind of heat we have to consider. Heat is coming not only through the walls, can also be going through the roof and then into the attic and then to the ceiling. Now we look at the convective heat transfer, and convective heat transfer always needs a fluid. It's either air or water to transport the heat. And we have, for instance, something which we call a leakage of an envelope, which are unintentional openings in the envelope, some kind of cracks. And if even the best construction has always like little, orifices, or what we call in Hawaii pukas, where the hot air can get into the interior wall. So we have this with the cracks. And we also have convective heat through openings in the envelope, for instance, in the windows or which we intentionally open up. And this would be, of course, for natural ventilation. But convective heat can also, is also effective in things which are like the AC, where here you would have a typical split system, where we have a heat sink inside, which is the evaporator, and the outside condenser, and we have a cold fluid. This one we are cooling up, it's going in, and then the heated fluid, we're taking out all the heat outside. So this is where we see like a fluid is a convective heat, which is very useful, of course, which we need. But now we're looking at the radiative heat transfer, and radiant heat transfer requires no flowing air and no direct contact. And consider, you're standing beside of a block of ice, you actually will feel cold, although there might be no air going back and forth. And of course, you cannot touch it. If you touch it, it would be conductive heat transfer. So here actually, let's say you are the body, and you are being cooled by your body, your warm body, radiating heat against the cold object here. If we if we put in some kind of obstacle where we block the infrared waves because they need the line of sight, we actually cannot have the radiant heat transfer. And the warm object here would stay warm. And radiant heat transfer is very important in buildings because we have sometimes very uncomfortably hot walls or hot ceilings. Although the air temperature inside might be comfortable, or it should be comfortable, but we are still, the warmer walls actually radiate heat against us, so making us more uncomfortable. Radiant heat is also important as heat goes through the solar heat goes through a window, heats up the interior, or gives direct impact on us. And therefore, we often right now, and specifically in the new energy code of Hawaii, we actually should have shades. And the shades, as you can see here, are blocking some rays. And remember, radiant heat transfer needs line of sight. So whenever we cannot see the sun, it's blocked in the shade. We don't get direct heat transfer from the sun, but we get secondary. We get, because the sun might heat all the objects around us, and therefore actually it is heating us up also. Something else also very important, which we are fortunately, which is modeled by the energy software, is a radiant heat through a roof, and that's when we have a radiant barrier. You might actually have a hot roofing material. We have some insulation, but still there's a lot of heat going on. The inside of the simulation is getting hot, and without a radiant barrier, heat would actually, impinge on the ceiling. Through radiant heat transfer, heat up the ceiling, and then actually we have conductive heat transfer to the living spaces. So this actually is the working process of a radiant heat. Now let's go to the BEopt program, which we'll be using here in our today's webinar. And the BEopt software, we have been using it at the University of Hawaii right now very successfully. It's really a fascinating software because it's so easy to use compared to other energy simulation softwares. And there are a lot of energy simulation software around. If you go to a website of the Energy Department of Energy, you will see basically hundreds of these products. And each actually has a specific, advantages. Each, of course, has also a price. But the nice thing here for BEopt, it is actually free. So we can download it. And it's based on an Energy Plus, which is a very powerful simulation engine. And I say a simulation engine, of course, it's not an engine. It's like a software engine, which cranks all the numbers. So we'll be using it, and again, you actually will see that it is, although it's very relatively easy to use, it still produces very powerful and very useful results. Here we have the fundamental steps of simulation, which you will find in almost all different simulations. The first one is we have to create a virtual model. And whenever you see something like 3D, you say, wow, this must be simulation. Again, like you can also make energy simulation by just a spreadsheet, or you can do it on pencil and paper. The second one is selecting site-specific properties. This is like where is your site located. The third one is to select specific energy efficiency measures. You will see this afterwards. And running the simulation afterwards, we display the results. So these basic 5 steps you can see all the time. Right now, the first one is we are creating a virtual model, and we'll be demonstrating afterwards with a real BEopt. And in BEopt, it will showing you have a very, very simple geometric model builder. And some other software, it's fairly complicated. And word of caution is here, don't put too much importance into the model. The model is actually only like, it tells the software where to put certain quantities, how big the walls are, and how big the ceilings are, and how big the windows are. But then actually afterwards we have to also put some properties on these 3D geometric elements. Second one is specific, site-specific properties. And this one is in BEopt, for instance, we have, we do have weather files with TMY files, which are available on the web. And you can download it. It's free of use, and it's representative of the site you are. And they have all kinds of different input variables in BEopt. For instance, here's like electricity, how important it is, how expensive it is, and all kinds of different other fuels. Then we also have mortgage information, because of what kind of interest rate. We have the project, because the real power of BEopt is optimizing alternatives. And you might have 10, 20, 100 different alternatives, which you can then automatically optimize. Here today, we are only saying, optimization of 2 alternatives. The third one is selecting building-specific energy efficiency measures. And this could be like the properties of the building in terms of building envelope, equipment, appliances, occupancy, and so on. And the third one, and here you see like one sample, we'll be going more into it. Third one is, the fourth step is to running. You just click a button and it just runs. Sometimes it takes 5 minutes, and we had cases with different software tools which cost a couple of days, depending on the sophistication. The last one is to display the results. And this is the output of the BEopt. We'll be seeing this later on. So what we want to do here right now is a sample simulation. And we have done this in the 3D outside. This is not BEopt. This is just outside, a very simple 3D CAD program with some shading. We have a gable roof here. We have it's a very small space. And here you see this is the perspective view, wireframe. We have it 35 feet long with 20 feet wide. And we have different window to wall ratio. And that means actually how big are the windows here relative to the wall. And we can define this one in BEopt. Here the back view, here the right view. So we'll be using this geometry in our sample simulation. So the geometry again here, this is north. It's the back side. North is always front. You see again like the different dimensions. We have 8 feet high rooms. 35 feet is outside. It measures from the outside and subtracts then the thickness of the walls. So right now I'll be changing to the BEopt software, and I will demonstrate certain characteristics of that. So here is our demonstration for BEopt. We start up here with the geometry, and right now I'm only very quickly demonstrate how you can make a 3D model. It's very easy, very simple. Again, other software much more complicated. You start here with the first floor, and you just make a model. And here you have the model. You can see it in 3D. I actually here have already the window to wall ratio of our sample, but this doesn't matter here. We have the first one we can make right now we can make the second. Whoop, I did this one a little bit too much, so I have to erase something. Okay, so you see this one is just the second model, the second floor of the model. You can have, in the first one, going back to the first one, you can make a garage. Put a garage here. Oop, this one, of course, is not. It's not small garage, only one garage. So you see how funny and easy it is here. Second floor, let's say we would like to have like a porch, like what we like to have in Hawaii. The back, we want to have a little lanai. So you see, this is the 3D modeling. We can create very quickly, we can create meaningful 3D models. And here there are different things, like we can have a gable roof or a hip roof. So then the next thing will be going here to, this one is the option page. Or let me first see, you know, the overall input page. This one is for Barbers Point Harbor. And therefore, actually, it gives us certain, you know, you can go in and you can create all kinds of, you can download all kinds of different weather files, which again, like, are provided by the Department of Energy. And these weather files are called TMY, the typical meteorological year file. They actually were put together for long periods of weather or weather observations and giving us a good average. Then you can, different things you can put in here. You can see here, for instance, that electricity, we use at a state average. It's about 29 cents per kilowatt hour. Then all these other things we can also give in, but right now we don't need this. Right now we're going on to the option page, and this is where the real work starts. We have a lot of options. These are option categories. And inside of the categories, we have subcategories. And these subcategories, for instance, here building, and the building has the orientation and neighbors. We can have walls, and then we have all the kinds of wood stud. We have all kinds of different walls here, which we can select. Let's say we make a wood stud wall, and inside of the wood stud we have different options. And then we can select the different options. So, and this one is also for ceilings. For instance, here we have roof material. You go foundation, thermal mass, windows, and then afterwards you get airflow, space conditioning. That's right now, this the first one was mostly the envelope. Now we can see the equipment here for cooling equipment. We have schedules, which are important, because even if we saw it before when we were calculating what is the energy, it's not necessarily how big the power draw is, how often, how long is it on. Then we have water heater, lighting, appliances, and all kinds of things here, which we need to get a comprehensive idea of the energy performance of the building. This one is the sample case, which I prepared before. Here you look, this one is the 3D, very easy. You see these are the different window to wall ratios, which we use which we defined outside. You first make the design and then come in and do this here. This one is the option page. And here you see, this one is the old and efficient design. And here is the proposed design. And the beauty here is that you can compare different alternatives. So what we, for instance, would do, we have an old and an efficient design. And then we have all the options. We enter all the options of our so-called old and inefficient design, which means we want to be better. So we put in first what is the existing, and then afterwards here we go to the proposed. And these proposed design have the same geometry and the same global setting, but different options. And again, the options are here, all these different things. We have the categories, subcategories, and inside of subcategories we have different options. Okay, so we actually have, again, like we have old efficient design, we have proposed design, and we go right now and choose whatever we want for the baseline. Old and efficient design would be the baseline design, and the proposed design would be the improved design. Let's go right now through. I have to go outside to the PowerPoint, otherwise switching back and forth would take too much time. So right now I have prepared a PowerPoint. I go back to the PowerPoint and we're going back through step by step. So going through representative efficiency, I don't give you all the options, and just to clarify the process, we're going through this right now. Here we have, these are, remember, these are from the BEopt, these are the categories. We have here the subcategories, and inside of the subcategories, we have options. There are options which come with the program, and if we are not satisfied with the different options, we can always do more options. We can just create them, because all the options are described by physical properties which go with the building design and the material. So you see, you know, we have used about 9 of that. We go through that in the walls. We have 2. We have the wood studs. We'll be looking at the exterior finish. Then we have the roof material, windows. We have air leakage. We have air conditioning. We have space. We have here water heating. We have lighting. And we have so-called plug loads, which are miscellaneous loads. Let's go through that. So the first one is the wood studs. You see here, this one actually, what we said, it's like a very common way to build houses here and walls here in Hawaii. And inside of the wood studs, we have insulation, which are between the beds. And we can have all kinds of different simulations. And on the right side, we have exterior wall, because it's also important, what is the exterior? If it's dark and, you know, or is it white and shiny, it has different properties to absorb heat. And the more heat it absorbs, the more penetrates the wall. So we even want to keep the exterior walls cool. Again, here from the wood stud, and insulation is the barrier. So if you have even hot air or hot outside the wall, we actually put a barrier that the heat cannot penetrate into the inside. Here we have the wood studs, and again, like this is a copy of the screenshot of the BEopt improved design, where we have like we opted for this one. This would be a 19 an R value, the cavity insulation. And the cavity insulation R value, I'm pretty sure everybody has heard it. It's not this is like the barrier. It's like a metric how big the barrier for heat transfer through the wall is. We see here, for instance, we have here the nominal R value, and here we have the R assembly. Because even though the material, the insulation material has an R19 value, we have wood studs. And wood studs, and we have some kind of shortcuts for heat, which we call also heat bridges. So the heat always finds a way to get into the house, but we try to make the insulation as effective as possible. The next one is the exterior finish here, and we have used for the improved design, we have used a vinyl light, and it has a solar absorptivity of 0.3. That means the associated word in terms of reflectivity is 1 minus 0.3 is 0.7. So this would say that 70% of the solar gain, of the solar energy coming on the wall is reflected. And this one is the emissivity, which is 0.9. This is just the amount of, it's the effective heat loss from the exterior wall to the environment. And what you want to do here in order to have an improved design, we would like to have a small solar absorptivity, means a high reflectivity, but also a high emissivity. These are 2 things which have to come together, because both are important. Next one, we have a cool roof, and we have the roof material here. We have different, we could have like black shingles, or we have some kind of ceramic stuff. Or we have the cool roof here, which is usually wide, high reflectivity. But we also, again, have to have high emissivity, because even if we have like aluminum, if you think it's a very high reflectivity, so it should be very cool, but this is not the case. certain aluminum alloys, they're very good in reflectivity, but very bad in emissivity. So if you think, hey, this is shiny, this is not getting hot, you step on it barefoot, you will burn your feet. So this actually is because the emissivity is very small. So in a cool roof, you want to have high reflectivity and high emissivity. And here you see we actually did not go for the whole thing. It's a high absorptivity, but here, you know, say, it might be that, you know, your association where you have the homeowner, they don't allow cool roofs. It still is, like in where we live. So we have certain shingles which are dark. But even right now, dark shingles does not necessarily mean it's bad performance. It can even be good performance with modern material. Next one would be the window area. And we have a window area here, which is big, or here on the right side, it's small. So I always make the joke, because I'm an engineer and not an architect, the best building for an engineer would be like with very small windows, because the heat gain is very small. Not like here, which is a lot of heat gain through windows. But of course, the architects will show us, hey, this is the value of the building is to make a beautiful building and make the occupants feel good. And I absolutely agree. This is something which I learned over a long time, that there's really, you know, the architects have a wonderful way of making beautiful building. So we have the window area, and we have also the window type. So here, we don't speak of the window area. This is given. We make a selection for the type of window here, and this one is a window which is 2 panes. It has a very low solar heat gain coefficient, not totally low, but it's still good, very effective. Next one will be air leakage, and this is you know, importance to the new energy code, and the air leakage is measured by a means of blower door. And this one is something which you put in your door and you suck out or you push in air, and then you measure how much air is actually sucked out or pushed in at a certain pressure differential. Usually pressure differential is 50 Pascal, 50 PA, P is Pascal, it's a measure for pressure. And the next one we'll see here, this one is a 5 air change at 50. This is 5 air change 50. 50 is 50 Pascal. There's also something sometimes, or blower doors might be 25 or 75 Pascal difference, but here we have 50, right? So this is an important input, and it determines how much air, how much heat gain is from convective heat gain through unintentional gaps in the envelope. Next one is the heat. It's a air conditioner, and we have like a central air conditioner. We have room, which is the least effective, and we have mini split system here. And for us, for our sample, we have a mini split system here, and we gave it a SEER reading of 23, which is a pretty good one. So SEER is the efficiency of how the equipment operates. The higher the SEER, the better is the efficiency. The better the efficiency, the less energy we use. We use this one for improved design. Now it comes to water heater. We can have either a solar water heater or a tankless water heater, or electric and gas water heater where we have a tank. So in our case here, we use the tankless water heater, and it doesn't have a tank, therefore it's called tankless, right? Makes sense. So it's a flow through. It's pretty energy efficient, but it's more like for low occupancy. If you have like a couple of people more in the house, would be not make a lot of sense. Here again, we have a tankless water heater, which we used for our BEopt model. And you see the energy factor is like it was 0.9% of the energy is actually transferred to making heat, which is very good. And we don't have necessarily any kind of heat loss. It's like a tank where the hot water sits for a long time. 8 is the lighting, which we actually have in our incandescent. We have incandescent, but I don't know, people still have it, I guess. We have LED, we have CFD, and we have fluorescent lighting. In our case here, we used 80% LEDs, so which is a very very effective, very energy efficient way, choice of lights. So this means 80% of the lighting fixture is with LEDs in our BEopt model for the improved design. The next one is the plug loads, and the plug loads is, you will see that at BEopt they have, they give default values which are based on standards. And the standards came up with, long research. It can be also regional, but this is usually how people behave. But we always have possibility of changing it by putting some kind of a fudge factor in there. And here you see we have like the multiplier factor, which is like the multiplier from the standard. The standard would be 1.0. We said, hey, we have we might have actually very low occupancy. We go like 0.5 because the standard plug load would be determined by occupancy and the floor area. So right now we are going back and we'll be looking at the results. Bear with me. I just have to bring up the BEopt interface. So right now we are back, and we go for our case study, and we look here. This one is the output. I've already run the model, so right now this one is results which are available. This one is the typical output screen of BEopt. On the right side, we have all the different options here, which you have to go down, and you can see all the different options which we have used in our modeling. And there are two different colors here because one actually is we have a reference. We have the optimized design, or the proposed design, and we compare to what we call the benchmarking, old or inefficient design. Let me just bring this one right now. And this one is a building optimization. This one would be only relevant if you have a lot of different simulation, hundreds of them, and it would give you an indication what is not only the option which has the biggest energy saving, but what is the option which is also the cheapest. And that's what we want to have. We want to have good energy savings for good price. Because sometimes you get a lot of energy savings, but it's expensive. So we would like to optimizing is both. We have to look at the cost to achieve the energy savings and the magnitude of the energy savings. So right now, let me get here to the lower left corner, which is like of our concern. So this is the results, and this is pretty neat because it actually gives us different types. And you see here, these are the different types. We can have like the source energy, utility bills, which we have right now, the site energy, electricity, all the different fuels we can use, the carbon dioxide emissions, the loads not met, HV capabilities. Let's look at the site energy for electricity. This is the most intuitive. And what it does here is that it gives different indications of what the site energy pertains to. And here, for instance, you have the cooling, here the dark blue, and you have different things here, like the light, for instance, is yellow. And here it says this is site energy, this is kilowatt hours per year, and for people and we could also use it here for the source energy. And the source energy it's given a different metric. This one is here BTU per year, million BTU per year. It's different from kilowatt hours, but it can be converted. And the source energy is very relevant in order to give you an indication what is the environmental impact of our energy, because whatever we use at the site, it's called site energy, but in order to create this energy, you have to use a certain amount of energy. Here, for instance, for electricity, the source energy to site energy ratio is the worst because there's a lot of losses allowed. So from what we put in, for instance, for the Kaya power plant here, only 1/3 of the energy we put in terms of oil reaches us as the electricity at the site. So let me just go here back to the site energy. Whoops. I have to do a little because there's something like obstructing here. So this is site energy. It is kilowatt per site energy here, like at BTU per hour. I tried right now. I just have this one is the utility bills. So we see here this is our proposed design. And our proposed design is $2,135 per year. We have to pay for our electricity, which we use in the building. And in the old or inefficient design was $4,750. So we are saving about $2,500 per year in energy bills, but we had a lot of improvements. So we can always decide then, like, of course, for the energy, for the environment, it's the best to save as much energy as possible, to make it as much as energy efficient as possible. In addition to that, it's also the energy code. We have to abide by energy code. So, we cannot choose, hey, we don't want to do such and such. We have to abide by it if we make renovations on new buildings. But this one is, again, like this is a simulated effort, and in the new IECC, also Hawaii Energy State Code, is that we can have one compliance part is by simulation, and we just have to show that we can have a lot of flexibility how to put the new design in, but we have to show that the improved design is cost less in terms of energy cost as the old design. And but the old design would be like a reference design, which would not be the same as the old and efficient design here, but it's something which is defined in the energy code. And here, for instance, the proposed design is way less energy, has way less energy cost than the old design or the reference design, so we'll be fine. Again, like we would save $2,500 here per year. And then we have to see whether or not for us it would make sense financially to do that. So I stop the sharing here. I go back to my other thing. And we'll be summarizing. So we have summarized it here that, we've summarized, we have demonstrated a simple energy simulation with demonstration BEopt, and we've shown the basic design is very easy to use. And for right now, we have their use in residential building. It's a very powerful, it's a very effective, and I would really recommend it and encourage everybody to learn it because it's not that complicated and it can be very, very powerful and very, very efficient. And the biggest value that is not necessarily how does it calculate, how does it compare to the existing measured data. The big power is optimizing through the design alternatives, and BEopt is really good at that. You can have parametric runs, you can have optimization runs where you can compare a lot of different alternatives. So I'm a little bit over my 45 minutes. So if there's any questions, I will entertain them. Yeah, I just have to, I didn't see it on the chat box. Phyllis was just reading to me from Shane, the questions whether or not we can model outside issues. We cannot. That's again, like BEopt, that's a very good question. Some other software can. And for instance, some other energy software would then model obstructions like trees or different adjacent buildings which actually shade the building, which also has an influence on the PV generation. So these are much more powerful programs, which is not in BEopt. So no, with BEopt we cannot model outside. How much the cost of the software? This is very important. It's free. So go down and you can go down to the BEopt website and download it for free. That's a good price, I think. Taxpayers' money well spent. Okay, I think this completes our recording. I mean, our webinar. And again, like we'll be recording and we'll make the recording available to everybody. I wish everybody a good day and thank you so much for joining. And see you next week. And the next week We'll be speaking about the new Hawaii State Energy Code, which is based on the 2015 IECC Energy. It's important, it's great that, you know, just we have some people pushing this forward here. And so we'll be discussing, we're going through some basics, maybe just touching on how we actually can use these these energy code to our advantage as designers. So I thank everybody for listening, to tuning in, and we see you next week.